Syzygy episode 29, The Serendipitous Rings of Saturn. And welcome back to everyone's favourite astronomical podcast, Syzygy. My name's Chris Stewart, sitting opposite me at the microphone as ever, Emily Brunston. Hi, Emily.
Hello, hello.
So today we're going to be talking about what is my, and I'm guessing probably many of the listeners out there, favourite planet, which is Saturn. Now, it's my favourite planet because it's just so very, very beautiful. It's even got, Emily, did you know this? It's even got its own Twitter account. There's a Twitter account called A Little Bit of Saturn. And it only posts just images, like here's a little bit of Saturn's rings, or here's a picture of Saturn just from the side, or whatever it is. And it just, whatever else is happening in the day,
That's
a little
very,
bit of
very
Saturn
cute.
just cheers you up. So we're going to be talking about Saturn today, and in particular, some recent news about Saturn that implies that, well, things haven't always been as they appear for the big ringed planet. But I'm going to kick off with this one. I think we talked about this before. What's your favourite planet?
Well, we talked about Mercury.
That's right, we did.
Mercury's my super favourite.
We did a whole episode about Mercury, and yes, the revelation that Mercury, against all odds, is your favourite planet. Just remind us why that was.
Well, one of the fantastic reasons was the day is longer than a year. That's one of the really cool things about orbital mechanics.
That's right. That was weird, wasn't it? Yeah, okay. So you're into the quirky planets. Yeah, you like a planet which has got a bit of a sense of humour. But where do you sit on the idea of Saturn as... I mean, I guess if you were to put up pictures of the planets in our solar system, Saturn and Jupiter would have to be the most instantly recognisable, right? Jupiter because it's got that big red spot and the striations, the stripes and the storms and so on. It's just got this amazing turbulent beauty. And then Saturn because it's just got these incredible rings around it. It's immediately obvious. So where do you sit on Saturn being up there in the list of planets?
Well, I have to confess Saturn used to be my least favourite planet.
Really?
I used to have a real thing against Saturn.
How is that even possible? What have you got against Saturn? How could anyone have anything against Saturn?
I just got so annoyed that it was everybody's favourite.
Oh, I see. It's the favourite child, the darling planet of the solar system. And so that annoyed you.
It annoyed me a little bit. Yeah, I was like, there's so much diversity and wonderful things going on that we need to look beyond Saturn.
Is that a little bit like how many scientists look at astronomy that way? But you guys have got all the pictures. You guys have got Saturn, and we've just got insects that burrow into eyeballs and stuff, and it's not nearly as sexy. But anyway, so Saturn, not so much.
Well, I have to confess, I did have to change my mind, and it was one little NASA mission that changed my mind.
Yeah, which was?
Cassini.
The Cassini mission, which was just almost miraculous. I mean, it changed our view of this planet in so many ways.
It's impossible not to fall in love with all the pictures that Cassini has sent back from Saturn. And I have to say, I think we're really going to have to be very self-disciplined today and talk really only about Saturn and its rings. But obviously there are huge amounts of things. Saturn has really exciting moons. We sent a probe onto one of those moons.
There's a lot we could talk about.
So much, but
look, put a thumbtack in that, stick it into the wall, because we'll come back to there's some of those other really interesting things that came out of the Cassini mission. Because there is so much to talk about Saturn. But no, we're going to restrict ourselves to the planet itself and its rings for today, because some interesting stuff has come to light, which is that apparently the rings may not have been around for as long as we thought.
Yeah, so those rings, they're kind of even more special now. It might actually be that there's a very, very special time that we live in, that we actually get to appreciate the beauty of Saturn's rings, because we think now that they're probably only somewhere between 10 and 100 million years old.
And just to put that in perspective, I mean, you know, phases of life on Earth, you go back 10 million years, 100 million years, you're back into sort of the late era of the dinosaurs. Now, that is a long time ago. On the other hand, it's relatively short in terms of the entire history of the Earth and life on Earth. And so just thinking back to the dinosaurs, had they had telescopes, go with me on this one, that they wouldn't perhaps have seen rings around Saturn.
Amazing.
Yeah.
Dinosaur astronomers really lucked out.
Yeah, I mean, I'm now imagining a T-Rex trying to operate the telescope with his tiny little arms, and it just doesn't work. But look, if we imagine that that's possible, they wouldn't have seen, which I have this image of Saturn as being always and forever big ball with rings around it. And thinking about that for a moment, I'm guessing it probably wouldn't have formed that way. But I guess I would have imagined that the rings would have formed around the same time.
Well, that was one of our theories, and it's one of the theories that we're now having to seriously examine and think about, well, actually, if the rings are new, how on earth did they get there?
All right, let's unpack this. Let's pull it apart. So why don't we start with what's the idea that's come to light? What's the data? What's the research that has come to light that has shown that maybe these rings aren't as old as we thought, and maybe not going to stick around for as long as we thought.
So this comes back again to Cassini. Mm-hmm. So Cassini wasn't just on a mission to take amazing pictures of the rings and send them back and inspire us all back into loving Saturn. It wasn't really designed for me to fall in love with Saturn again.
Saturn didn't really need the help. Frankly.
No, but no. I have to confess I really have. But actually, Cassini had a lot of data and a lot of instruments on board. And actually, this is really kind of poetic because in the very final, what they actually call legitimately the grand finale of the Cassini mission was that it did these orbits very, very close to the planet Saturn itself, in between Saturn and the rings. And the data that it was sending back during this time was analysed to actually try and measure the mass of Saturn and the mass of the rings.
Because that's the first time that's been done, hasn't it? That no previous mission to Saturn had sort of, done a dive down into and amongst the rings and between Saturn and the rings.
No, and it's a one-way mission, right? Well, there was a few orbits. I think there were 22 orbits in total. And 6 of those we managed to be in contact with Cassini whilst it was going through this orbit. And then Cassini sort of plunged deep down into the atmosphere of Saturn and was gone forever.
Just remind me, Cassini, when has all this happened? When did Cassini take off and when did it meet its fateful end?
So there's a few dates and they're pretty sparse. I mean, we know that we launched Cassini in 1997. Mm-hmm. Took quite a while to get out to Saturn.
Because Saturn's a long way.
It's a long way away. So it arrived in 2004 and then operated for 13 years, taking these fantastic images, making all these wonderful measurements. And then it was September 2017 that this final grand finale, if you like, event happened over the course of a few days.
Was that part of the original plan, or was it, look, we're running out of fuel, where the orbit's going to decay anyway, let's do one last great thing? Or was it, hey, here's something we've never done before. We've been up there for, I don't know, however many years it is, 13 years. Let's go out with a bang. Did they have to do that? Could it have gone on for another 13 years, or were they coming to the natural end?
The satellite was coming to the natural end anyway, but it was planned. And one of the reasons why we actually decided to throw Cassini into Saturn was because we are very concerned still about contaminating the solar system. And if we have any inkling that there might be life forms past, present, or future on any of the moons, say, of Saturn, like Titan, then we don't really want to go interfering with that, because despite our best efforts, there's probably some form of life on most of our spacecraft that we send out there.
Yeah. So rather than crashing it down or trying to touch down on the surface of one of the planets that could have some really interesting stuff on it, let's just throw it down into the depths of Saturn and wave goodbye on the way.
It's kind of like the incinerator.
Yeah, exactly. Okay, so talk us through then this data. You were saying that in doing these dives down through the rings and in between the rings and Saturn itself, Cassini was able to get some data that we'd never had before. So talk us through that.
So we were able to be in contact with the spacecraft and by radio link. And from that, the spacecraft was able to tell us things about the gravitational field that it was experiencing. I'm very much personifying the spacecraft at this point.
But why not? I mean, it met a very romantic end, so I think it deserves a bit of personification.
Yeah, so we got lots of really precise measurements of the gravitational field of Saturn, very, very close to the planet, which we hadn't had before. And what we're able to do is compare those to the measurements of the gravitational field further out, say beyond the rings, and basically do a difference measurement. So use that gravitational field to work out, okay, what is the mass of Saturn plus rings? And then from the newest data, what is the mass of Saturn only? Therefore, the difference is the mass of the rings.
Makes sense. I mean, when you're further out, you can't really tell much of a difference between a planet with rings around it and a planet without rings around it. You're just measuring the gravitational attraction of this lump of stuff underneath you. But get in between them and you've got the rings pulling you one way and the planet pulling you with much more significant force the other way. And presumably you can measure the difference. So what does that do for us? Okay, we've measured the mass of some rings. So what?
Well, it turns out that the mass of the rings was a lot lower than we thought it was originally. And to give you some idea of scale, so Saturn's big, right? It's like 100 times the mass of Earth. You could squeeze something like 763 Earths inside of it if you pack them well enough.
Quite a few. It's not as big as Jupiter, but it's a gas giant.
Yes.
It's a big, big planet.
Very, very big, which means that Saturn itself has a mass of something like 5.5 times 10 to the 26 kilograms.
Which is a very big number.
Very, very big number.
Okay, so 10 to the 26, let's remember that. 10 to the 26 kilograms, as opposed to the mass of the rings?
Which is something like 10 to the 19.
So we're talking 10 million times bigger. The planet is 10 million times bigger.
Than the rings, yeah.
Wow, okay. So that's quite a lot.
So the rings are tiny, actually.
Yeah. So in contrast to the Earth and the Moon, I mean, the Moon's much smaller than the Earth, but it's not 10 million times smaller than the Earth. So the rings have got a lot of stuff in them, but they're very, 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 very small and light.
Yeah. And so despite the name of 10 to, the 19, so we can say about 15 sextrillion. That's one of my new words for today.
Excellent. Well done.
So 15 sextrillion kilograms. Despite that sounding like an awfully big number, it's actually something like only half of one of the small moons of Saturn, called Mimas.
So that puts it in perspective that Saturn's got a bunch of moons.
It's got a lot. Mimas, you might remember as being the Death Star moon.
Oh, yes. Yeah. Okay. Picture in the show notes. We'll dig that one out. But yes, it looks like it's got one of those great big dishes on it that sends out the death ray to blow up planets like the Death Star does in Star Wars. Yeah.
But it's not a star, it's a moon.
It's a moon.
Tiny little moon of Saturn. Yeah. So basically, if you add up all of the stuff that's in the rings, then you only get to about half the mass of Mimas.
That small moon. Not even one of the big ones.
No.
Okay. So the rings are beautiful and you can see them really, really well, but there's not a lot of stuff in them.
There's not a lot of
stuff
in them.
It's very dispersed.
Yes, yeah. So what we're really talking about is what the rings are actually therefore made of. Mm-hmm. So we know that they're made of ice, water ice mostly, and that's very, very reflective, which is handy, which means that it reflects light from the sun and we can see these beautiful rings.
Yeah, hence they're so visible, yeah.
There's tiny little bits of other things like silicates in them, but for the vast majority, they're just particles. So something like the size of maybe cigarette smoke size particles.
Really? Wow.
Up to about 1 meter. That's kind of the size range of the particles in the rings. So they're not continuous. They're not sort of any one lump of stuff, but they're lots of little things that are formed into like a nice disc shape.
Right. Smoke, dust, gravel, and rock.
Yeah.
Yeah. Okay.
And what's really cool about it, and this is something that I started to think about a bit as well, is that when you see gaps in the rings, so the most famous gap is called the Cassini division, and it's not after the satellite, it's after the original Cassini astronomer who started to discuss rings of Saturn and what they might be all about. So we've got two bright rings. You've got the A ring and the B ring. In between them is this really dark patch. It's actually not empty. It's just a density change.
Okay.
So you have really high density of ice, which makes it look quite bright in the A ring and the B ring. And then you have a really low density of material in that gap. And the reasons for all the gaps in the rings are just fascinating as well.
Aren't they, like some of them, aren't they to do with the fact that there is a larger chunk of stuff which is sort of clearing rings out of the way? Or is it more complicated than that?
No, that's pretty much, we've got lots of little moons, or even moonlets, if you like, kicking around in Saturn's rings. Some of them are so tiny we haven't really even found them yet, but many of them we do know about. And these moons, some of them are shepherd moons, which I think is a lovely term.
What's a shepherd moon?
A shepherd moon. So shepherd moon basically herds material in the rings into particular formations. So sometimes there's a moon that kind of has cleared a little space around it, and that's formed a dark patch in the rings. But sometimes it's the moon's gravity that's kind of pushing material into a particular shape, into a particular ring.
I can imagine a moon sort of ploughing into the rings and pushing stuff out of the way. but you can also imagine a moon sort of, as you say, dragging stuff around with its gravity and influencing in kind of interesting ways over long periods of time the structure of those rings.
Yeah, and there's a beautiful image from Cassini, sort of a little gif, if you like, of Pan and Prometheus, so two of these moons, and they're in each side of the ring, and you can see that they're both shepherding. I think actually only one of them's technically a shepherd moon, but they're causing the material to form into this bright ring, and the inner moon is even causing these spiral waves to go through the rings, and it's just gorgeous.
So one's shepherd, one's sheepdog. Yeah. Go with that. Again,
yeah,
astronomy, you can
very,
have that
very
one.
Cool.
Yeah, nice. So we have the structure of the rings, but the bottom line from these new measurements is that it doesn't weigh a lot. Like, it's not got a lot of mass in there. Half as much as one of the smaller moons. Okay, so we still kind of come back to, well, that's interesting, but so what?
Well, there's two things that are so what about that. First of all, we know that the rings are still super bright. So that means that the ice that's in the rings must be reasonably young.
Right. Is it
Basically, it gets dirty over time.
A bit like when snow falls, right? When you've initially got a covering of snow outside in winter and it's pure white and it's beautiful, and then after a couple of days, it just, particularly around roads and things, it just gets dirty and turns into this brown grey slush. Similar kind of thing with ice in rings around planets.
Similar, yeah. So we have interplanetary dust in our solar system. It's really, really tiny, tiny particles. It's much, much smaller than, say, the dust under your bed. But it's kind of bits of material that was left over from the formation of the solar system, or if there's any kind of cataclysmic event in the solar system, it adds more dust. And that
Space ain't empty, is what you're saying.
Yeah, it does build up over time. And one of the early findings of the Cassini mission was that there was quite a lot more dust around Saturn than we thought there was. So if these rings are super bright, it means they haven't collected all that dust yet and become dirty.
So I'm guessing then that you could use that to work backwards. You could say, well, how bright are they? But the brightness would also depend on how much stuff is there.
Exactly.
Okay.
Yeah.
So you put all of this together and you say, well, there's this much stuff and it's this bright. So you're working backwards to then figure out, so how old is it?
So, yeah, and then you need to know both of those things together. And so that's why this mass measurement's really important to find the age. Basically, if you're older, then you have to have had more mass to begin with. So we can link the mass and the age of those particular rings.
So working that one backwards, then you get to that age of, you know what, maybe Saturn's rings are, at most 100 million years, did you say?
Yeah.
Age of the dinosaurs.
Not that old.
So back then there wouldn't have been rings, and then there were rings. So where'd they come from?
Well, that's a really interesting question. It's really, really... And so what we are using this information for is to try and understand, where did the rings of Saturn come from? It's not kind of a definite, this is exactly where they came from, it's exactly from this period in time, but it's kind of a clue, if you like, a piece of evidence. There's a couple of options. So one possibility is that there was a comet that came from the outer solar system and was basically torn up because it came too close to Saturn. That kind of works. We know that comets are mostly ice. Mm-hmm. It kind of has some of the same properties, but we probably need to know a little bit more about the material that's in the rings. We need to understand a little bit about where things are distributed.
Would that make sense in terms of the mass? Are comets that big?
Yeah, I think, they are that big. So remember, the moon that we're talking about is really little.
Yeah, true.
It's not moon size.
Yeah. So that could have been a comet. And of course, these things do happen. It was a comet that bashed into Jupiter years ago, wasn't it? What was that?
So Jupiter ripped it apart, and you saw all the little bits of each little particle, a bit of the comet just smashing into Jupiter, and it was amazing. You got this trail across the surface.
And that was wild. So that was either an incredible coincidence that should happen just at a time when humanity has telescopes that we can train on a big planet and watch that in real time, or it actually happens reasonably frequently, in which case it's a plausible explanation for where Saturn's rings came from. So, okay, there's that.
Or one of the other ideas, at least working with this timeline, is that there may have been an icy moon around Saturn. Some kind of event happened from what that event might have been.
It sounds very drastic, doesn't it? Some kind of event. Bum, bum,
Yeah. Well, if you have a planet and a moon system, then they're normally fairly stable in their orbits, and they'll merrily continue on like they have done since their formation. But if there was an icy moon around Saturn and something happened, another object came in from the outer solar system, for example, hit it. Centaurs are one of the objects I've seen mentioned as well.
What's a centaur?
That's
a half man, half horse. What are you talking about?
Kind of a big comet.
Okay, right. Big comety thing.
Yeah. Came in. So it would have to be something happened, and then that planet was basically, again, ripped apart by Saturn's gravitational force, and therefore that moon formed the rings.
Right. So it could have been an icy moon. Again, wouldn't have to be a big one, just a little one.
And we've got some icy moons around that area as well. Jupiter has Europa. Yeah, Io is the volcanic one. Europa, the icy moon. Saturn has Enceladus, which is quite icy. So
it could have happened.
Yeah. Something horrible happened to one of those moons, and some of the surface came off, formed the rings.
Okay, so that's also plausible. Yeah. Any other theories?
Well, the other ones are kind of based on the idea that the rings are much older. So either they were once a moon. There was even a name for this moon that may have existed. It's called Veritas. Mm-hmm. I really like it how astronomers name things that may or may not have existed.
And Veritas, I mean, that's Latin for truth, isn't it?
Yeah, well, it's there was a Roman goddess, I think, as well.
Okay.
Something to do with water.
Yeah. All right.
And,
so they can name things that never existed or might not have existed, but coming up with names for things that we've just discovered around stars on the other side of the galaxy, we'll just give it some numbers. Yeah. Well done, astronomers. Come on, get your priorities right.
Yeah, so that kind of still fits in what the previous theory I said, with just when that moon broke apart is kind of the idea. And the original theory was kind of, well, maybe this was just part of Saturn's formation. I mean, maybe it was just the stuff left over from Saturn. Like the planets are the stuff left over from the sun, maybe the rings were stuff left over from Saturn, that because of the particular order of the way the moons have set themselves out meant that it just never really formed into its own moon.
Right. And so that would have been the theory that sort of said, look, basically the rings have been around for as long as Saturn has, give or take, much, much older than the 100 million years. We're talking billions of years at that point. And that was a theory which was prominent up until these measurements. Is that right?
Yeah. So there's we're starting to move away from that kind of idea based on the evidence that we're seeing so far. So it's very exciting.
Yeah. And this new evidence is compelling. I mean, it's blown the old theories out of the water, or is this, well, it could be this, could be that?
I think it's very good data, and we have to trust that. I think it's more we're building a model of what Saturn is like, and this is just another piece in building that model. It's incredibly difficult to work out the history of the universe, our solar system, even our sun, based on we're only getting a snapshot of it at this point in time. We can't just push rewind.
Yeah, you can't wind the camera backwards. And, in terms of even just having images, we've only got at most, images through telescopes going back a few hundred years at best to be able to see, well, yeah, there were definitely rings around Saturn a few hundred years ago. Beyond that, we can't really ask anyone. No one knew.
Yeah, so we don't have the archaeological record that you do, say, for the Earth when we come to looking at the planets. But what we do is able to measure very, very precisely lots of different characteristics and then input those into models.
Yeah, I mean, and the models have got to be able to explain all the stuff that you see. If a model can't explain, as we were talking about with the rings, right, there's very little material there and it's very shiny. And the model's got to be able to explain that. And if it can't, if a model that says, well, these things have been around for billions of years, yeah, but it wouldn't be shiny anymore, then that model doesn't work quite so well anymore. It's got to fit.
And a great thing about this particular piece of research was that it also added some more data that we can input into models as well.
Cool. What sort of stuff?
So we're also able to answer the question, actually, how long is a day on Saturn?
Okay. I, naively, and a lot of stuff I say on this podcast is pretty naive, I know. But naively, I would have put how long is a day on Saturn into the big box of, does astronomy already know the answer to this question, yes or no? And I would have put it into the yes, surely we know how long a day on Saturn is. Because it's a big planet and we can see it really well. Like, can't you just measure that?
It seems like a really easy thing that you go and measure.
Yeah.
It's actually really tough in the case of Saturn.
Why?
So it's difficult measuring the length of a day, which is how long a planet takes to rotate upon its axis. It's difficult to measure that for gas planets.
Because you can't see much detail?
Yeah,
Right.
you're looking at the surface and you've got to have really good surface features that you can track for a very long period of time.
It does kind of occur to me that all the images that I've seen of Saturn, where you've been going, wow, look at the rings. If you look at the planet, it's kind of featureless in a way which Jupiter isn't. I mean, Jupiter's got stuff all over it. And I'm assuming that all the clouds and storms and crazy turbulence on Jupiter is rotating around at roughly the same speed as the stuff that's underneath it.
Yeah, roughly, yeah.
So a day on Jupiter would be relatively easy to figure out. But Saturn, apparently, not so much.
Yeah, although even Jupiter is really hard because different parts, depending on where you are, if you're near the equator, if you're near the poles, different parts go around at different rates.
Yeah.
So what we actually use for the other gas giants is a measurement of how their magnetic field rotates.
Right, because... So are the other planets a bit like the Earth then, in that the magnetic North and South Pole, for example, don't necessarily coincide with the axis of rotation? That magnetic North is sort of sticking out at a bit of an angle from the top of the Earth, and that will go around the axis of rotation. So you could sort of see that difference and be able to say, okay, it's just done one full revolution, that's a day.
Yeah, it's almost like a lighthouse effect with
the
magnetic field, so you can see it go blip, 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 blip. By.
Cool,
yeah.
Okay.
Yeah, it turns out Saturn was not playing game with that measurement either.
Saturn, what are you doing?
So Saturn's magnetic field, as much as we can tell, is pretty much bang on its rotation axis.
Typical. You know, it's always got to be the centre of attention, doesn't it? Look at me. So what have we got then?
Well, we did have some idea of how Saturn rotated based on some of the interesting waves that we saw going through the rings, but it wasn't a super precise measurement, and we wanted to nail that down, really.
So you're trying to guess the period of rotation of the planet itself from the effects on the rings and the structure that would put into those rings.
Yeah, and so we were able to measure some of those spiral waves in a much more accurate way. And this is a really cool word. This is my second cool word for the day. This is a technique called chronoseismology.
Oh, I like it.
Chrono with a K.
Chrono with a K?
Chrono with a K.
So I would have said chrono with a CH, chrono meaning time, but maybe chrono with a K meaning time as well? I don't know.
I'm not sure the origin of the word, actually.
Anyway, but it's
got seismology in it, which always gets me excited as well.
So I'm guessing chronoseismology means seismology based on some kind of periodic time sequence of rotation, that kind of thing?
Yeah, oscillations is kind of the fundamental part.
That's the word I was looking for, yes. Yeah. Periodic time sequence thing. Oscillation is a word, yeah.
So Saturn has oscillations in its interior, and it turns out that those oscillations affect the waves. The waves that travel then through the rings. So you can observe how oscillations in Saturn affect those kind of spiral density changes all throughout the ring structures.
And those oscillations are related to the period of rotation of the planet?
Yes, yeah. So we could basically you're looking at clumps of material that are a little bit denser traveling around with the rotation of Saturn, and you can watch those kind of clumps, or at least watch the effects that those clumps have on the ring structures.
Cool. So, okay, Cassini's gone in there, had a really good hard look. What's the punchline? How long is a day on Saturn?
A day on Saturn is 10 hours, 33 minutes, and 38 seconds.
Wow, that's really quick.
Very quick.
For a very, very large planet. It's really whipping around.
Yeah, it's not the record holder. Jupiter still holds the record.
Really? How long's a day on Jupiter?
9 hours and 56 minutes.
Wow. So they're really spinning around very fast.
They're whipping it around.
So the outer, I mean, they're huge, these planets. So the outer surface, if you can, I don't know, do they even have surfaces? Like, how do you define if it's a gas giant? How do you define where the surface is? There's got to be some definition of that, surely. But the outer surface or layers, they've got to be moving incredibly fast.
Yes, yeah. So whipping around.
Wow.
And what was really cool was that we know that the equatorial atmosphere, so this is part around the equator of Saturn,
where it's going to be moving fastest.
Yep, it moves faster than the inner layers of Saturn and even the core of Saturn.
Okay. I don't know how that works. How does that even work?
So, there's this thing called differential rotation, and we know it on the Sun, on Jupiter, where you know that the equator might rotate faster than the poles.
Yes,
right?
that makes sense.
Now just imagine that instead of doing that over the surface, that change, you now got changes where each shell inside the object is rotating at a different speed.
And again, I can imagine that, but what I'm having difficulty imagining, like I can imagine in my mind a core rotating quite quickly and the outer layers struggling to keep up. What I'm having difficulty imagining is the outer layers going faster than the inner bits.
Yeah.
How does that work?
It's amazing. Well, it's all part of magnetohydrodynamics.
Of course it is.
Of course it is.
I was just
mostly
going to suggest
hydrodynamics,
that's got to be magnetohydrodynamics. Surely.
Yeah, it's a lot of maths. It's really tough. But by using this, we can start to unpick a little bit about what Saturn is like on the interior, because you get really good measurements of all these different layers rotating. We know that Saturn rotates kind of like a solid body once you get in a particular depth. Saturn, it turns out to be about 9,000 kilometers.
Okay.
Once you're down 9,000 k's, then the whole of Saturn rotates the same.
It's like a lump.
Yeah. And we know that was true for Jupiter as well. It just turns out that for Saturn, it's a lot deeper before you get that solid rotation. And that's very interesting and a new result that I don't think we were quite expecting.
Cool. Okay. So from the Cassini mission then, we've got a couple of really cool results. We've got that the rings seem to be a lot younger than we thought. And we've got this quite interesting revelation about the fact that Saturn is really rotating very quite quickly, which is news to me. But does it tell us anything? So if you go back 100 million years, if the dinosaurs had they telescopes, wouldn't have seen rings around Saturn, let's say, then does that mean that the rings are a little bit more transient than we had imagined as well? That in the future, Saturn may not have rings?
Definitely. So we do think that they're a limited time offer, basically. So if you want to go and check out Saturn's rings,
go now.
You need to do it within the next 300 million years.
Time's running out, kids. 300 million years. So all up, we're talking, 500 million years-ish, thereabouts, that these things have been around, which happens to coincide with when we can look at them.
Yes.
And be inspired by them.
Yes.
That was good luck.
It's very good luck. And actually the fact that there's less mass in the rings than we thought there was probably means that lifetime's even somewhat reduced. And that's because the rings of Saturn, they're slowly sort of melting, well, not melting, but they're slowly evaporating away. And there's two different ways that they do that. So the first of all is, this was quite an exciting thing that I was reading about. You know that Saturn's rings have an atmosphere.
Hang on, what?
Yeah. So sunlight hits the ice. It doesn't melt into a liquid. It just goes straight into the gases. And then you get hydrogen molecules, oxygen molecules, which sort of then clump around the rings. But eventually those are going to be lost into space.
Is that a bit like how when comets come around towards the sun, and comets, as you said before, mainly made up of ice, that as they heat up, they get a bit closer to the sun, that's where you get the comet tail from coming off the back, that's the gassing off of the ice from the comet. Is it a similar kind of thing? Yeah,
it's a similar thing. It's just a lot slower for the rings because they're further from the sun than, say, comets when they come into the inner solar system.
Right. But presumably that then means that, that's a one-way process, ice turning into hydrogen, oxygen, and then that dissipates off into the cosmos, and eventually you've got no more ice in the rings.
Yeah, well, and even more interestingly is that the rings themselves, when you talk about the edges of the rings, whether that's the inner edges or the outer edges, at those edges you still get things forming. So they are dynamic in the sense that the rings themselves are coalescing into small bits, and they get bigger and they get bigger, and eventually these become moons. And those moons then carry off mass if they can move out beyond the orbit of the rings and become just kind of moons in their own right. So that's also taking mass, if you like, away from Saturn's rings.
So that's what we think is going to happen over the next couple of 100 million years, is that the rings will slowly but surely both degas off into the cosmos and clump together to form moonlets and maybe even, real bona fide moons. But there won't be rings anymore. There'll be gas in space and big lumps.
So do you think Saturn will be your favourite planet then?
Oh, I don't know. going to have a look at it and see.
Saturn without the rings just doesn't quite have
It
the
doesn't
same
really.
appeal,
I mean,
does it?
no, it doesn't. I mean, it is incredibly iconic. If you didn't have those rings, I don't know. It doesn't have the surface features of Jupiter. It's not. We can't go and land on it like Mars, so it's not our next door neighbor. I don't know. Maybe Saturn will just become just Saturn.
So maybe Saturn is a one-hit wonder.
And that brings us to the end of another edition of Syzygy. As ever, this has been produced in the office of Emily Brunsden here at the University of York, and we're very thankful that they've set this up so nicely for us here in this very plush and well-appointed studio that we have in Emily's office. Emily, thanks for joining me on the microphone once again. Can you tell us, is there a way for people to contact us if they wanted to get in touch and maybe, I don't know, ask us a question?
Oh, Chris, you're in luck. There are lots of ways to contact
Excellent.
us.
Tell us about them. What can they do?
So if you're in the Tweetyverse, then you can get us on @SyzygyPod. That's SYZYGY pod. If you want to check out our beautiful website, and definitely go and have a look at some of these pictures of Cassini, because they're just so beautiful.
They are. I mean, we joke, but Saturn is a pretty extraordinarily beautiful planet, and Cassini really did a good job of that.
Get them while they last on syzygy.fm.
Yes, indeed. And of course on Facebook, facebook.com/SyzygyPod. In fact, we're pretty much SyzygyPod anywhere that you want to go and have a look and think, I don't know, is Syzygy there? Just search for us as SyzygyPod and you might find us. The other way that you can get in touch with us, or that you can make contact with the show, is through a little site called Patreon, patreon.com. And it's a way that you can help out the show. If you enjoy what we do and you want to help us to do even bigger and better things in the future, then consider becoming a patron of the show. What that means is that every month or so you can sling £1 or a nice shiny American dollar our way, and if enough of that builds up over time, then that gives us a chance to do this in bigger and better ways. Like in the last episode, Emily suggested that maybe we should go and watch an eclipse in 2021 down in South America. 2020, not even that far away. That would be awesome. So if you want to support us to do fabulous things in astronomy podcasting, patreon.com. But of course, the other thing you can do is just simply tell your friends. And in fact, that's even better. It helps us to rise up through the noise of the podcasting universe, and more people can hear about us. So leave us a review on Apple Podcasts or on Spotify or wherever you get your favorite podcast, and tell the world how much you enjoy the show. Otherwise, we'll be back again in about a week or so's time for a bit more astronomy goodness. We'll see you next time in about a week.
See you later.
Bye. What's a good word other than disappearing, transient, fleeting? Fleeting rings of Saturn?
Saturn's rings for a limited time.
Saturn's rings are a limited time offer. I mean, I like it, but it's a bit long. Ephemeral? Ephemeral's a good word. Evanescent. Fugacious. That's a great word.
Other way, Chris, other way. That got dropped on Friday. That is Gamma Doradus, which is the prototype star of the whole class of stars that I work in, and one of my favourite stars in the entire universe.
So Gamma Doradus stars are named after a star called Gamma Doradus.
Yep, lots of variable stars.
That seems confusing to me.
And then they name the whole class after it. Well, Cepheids are an example.
Oh, really?
Yeah.
So there's a star called...
I think it's Delta Cephei.
Oh, okay. Yeah. There you are. All right, well, what do I know? Obviously, not a lot, clearly.
But yeah, isn't it beautiful?
It is, it's lovely.
I even showed my first years and said, look, what is it? What is it? It's a star. Yes, but look, it's not just got one frequency. You can see the beating.
Yeah.
You remember waves?
Yeah, you can actually. That's very cool. All right, that needs to go on a t-shirt. One day when we're popular enough, we'll have merch.
Gammador merch.
Gammador merch. Get your Gammador t-shirts here.
I can think of at least 4 people who might be keen enough to buy one.
Well, 2 of them are in this room.